The year 2026 began with a systemic shock that shattered the industry's collective optimism. Fable 5, the most resource-intensive model ever conceived with an estimated compute cost exceeding $15 billion, failed to deliver the anticipated leap in general reasoning. While parameter counts reached unprecedented heights, the delta in performance compared to its predecessors was marginal, signaling the arrival of the scaling wall. This phenomenon, which we identify as the point of diminishing returns in brute force compute, has forced a fundamental re-evaluation of AI investment strategies. For the information management professional, this is not just a technical failure, it is a signal that the era of growth by size is ending. We are witnessing the limits of the chinchilla scaling laws when faced with high-entropy reasoning tasks. This crisis has exposed the vulnerability of architectures that rely solely on massive token consumption without structural innovation. But does this mean the road to AGI is blocked? Not necessarily. It means the map in using is now obsolete. By the end of this lecture, you will hold the blueprint for the next era of AGI architecture that bypasses this wall entirely. To navigate this pivot, we must cultivate a new level of AGI literacy. As strategists and architects, our focus shifts from simply deploying large language models to designing systemic intelligence. This involves a strategic roadmap that moves beyond the LLM-centric view and embraces modular, agentic, and neuro-symbolic approaches. We are transitioning from the large-scale era to the structural innovation era. In this chapter, we will deconstruct how the industry is pivoting from raw parameter density to algorithmic efficiency and cross-domain reasoning capabilities. This transition requires a deep understanding of the intersection between data quality, system architecture, and real-world deployment constraints. We must ask ourselves, how do we achieve AGI-level performance with finite resources? This lecture is designed to answer that question by providing a systematic framework for the 2026 landscape. We will look at specific frameworks like the Agentic maturity model and new benchmarks that replace static MMLU scores. The scaling laws haven't just slowed down, they've fundamentally changed their nature, and understanding the history of this shift is our first step toward mastery. Looking back from 2026, we can clearly see the trajectory that led us here. In 2023, the world was mesmerized by the conversational capabilities of GPT-4, sparking a race for compute dominance. By 2024, the focus shifted toward efficiency with the rise of high-performance small language models, or SLMs, as enterprises sought localizability. However, 2025 marked the beginning of the data exhaustion era, where the supply of high-quality human-generated text was depleted, forcing labs to rely on synthetic data and self-play reinforcement learning. This was the point where the scaling laws began to bend. We saw models that were larger but not significantly smarter, leading to the 2026 plateau we currently face. This timeline proves that data exhaustion is not a future threat, but a present reality that is forcing a radical shift in how we define enterprise intelligence. The reliance on synthetic data created a model collapse risk that only the most sophisticated architectures could overcome. We are now in a phase where inference time scaling thinking longer, not just being bigger, is the new frontier. This timeline proves that data exhaustion is not a future threat, but a present reality that is forcing a radical shift in how we define enterprise intelligence. As we stand in 2026, the gap between research labs and enterprise adoption has fundamentally changed. While labs are still chasing the elusive AGI, corporations have shifted their focus toward the agentic shift. We no longer view LMMs as mere chatbots. We treat them as the central reasoning engine within a complex ecosystem of tools, memory, and sensors. The current state of AI maturity in the corporate sector is defined by reliability and orchestration rather than raw creative output. Enterprises are now demanding reasoning as a service, where the model's ability to use an AP correctly is more valuable than its ability to write poetry. This is the transition from vibe-based AI to engineering-based AI. We are seeing the emergence of the agentic maturity model, where systems move from simple automation to autonomous problem-solving. But why exactly did the scaling laws fail so spectacularly for Fable 5? Understanding the mismatch between parameter count and real-world utility is crucial for any IT leader. In the next chapter, we will deconstruct the math of parameters versus reality to find the hidden cracks in the foundation, starting with the actual physics of current scaling laws. For years, the AI industry operated under a seemingly unbreakable law. The more compute, data, and parameters you added, the smarter the model became. This was the chinchilla optimality legacy, which suggested a balanced ratio between model size and training tokens. However, as we approach 2026, we are witnessing the great decoupling. Increasing parameter counts is no longer the primary driver of emergent capabilities. In fact, the cost of training a 100 trillion parameter model is hitting a wall of diminishing returns where the marginal intelligence gain per petaflop is plummeting. We are moving from a brute force era to an efficiency era, where the architecture must do more with less. If the scaling laws of 2020 were about size, the laws of 2026 are about structural optimization. But this leads us to a more pressing problem. We are literally running out of things for these models to read. Have we reached the absolute ceiling of human knowledge available for training? The data wall is the silent killer of the scaling dream. Historically, models thrived on the massive ingestion of the public web, but by 2026, every high-quality book, research paper, and forum post has been consumed multiple times. To bypass this, labs are pivoting to synthetic data generation where AI trains on AI-generated content. But this introduces a model collapse risk, a recursive feedback loop where errors are magnified, leading to a loss of variance and factual decay. Research indicates that without gold standard human data to anchor the training, models quickly become detached from reality. This is why we see a shift from big data to deep data. The focus is now on quality over quantity, using specialized reasoning chains rather than just more tokens. But even with perfect data, the physical infrastructure is screaming under the pressure. Is there enough electricity on the planet to sustain the next generation of training runs? The energy cost of intelligence is the final frontier of scaling. In 2026, training a state-of-the-art model requires dedicated nuclear or massive renewable power facilities. We are seeing a transition from H100 clusters to Blackwell-based liquid-cooled mega data centers, yet the energy efficiency of the transformer architecture remains a concern. When we compare the marginal intelligence gain of a GPT-5 class model against the exponential jump in gigawatt-hours required, the ROI becomes questionable for many enterprises. This power wall is forcing a shift towards specialized silicon and neuromorphic-inspired architectures that prioritize energy per inference. The era of growth at any cost is ending. We are now in the era of intelligence per watt. This physical constraint is what truly defines the AGI timeline. But what if the problem isn't just the hardware, but the very way the transformer thinks? Let's look inside the architecture to see why it's hitting a logical ceiling. The standard transformer architecture, which has dominated AI since 2017, is facing inherent structural bottlenecks. The most significant is the quadratic complexity of the self-attention mechanism. As the context window grows, the compute and memory requirements explode. In 2026, while we have models with multi-million token windows, the lost-in-the-middle phenomenon persists: the model's inability to effectively retrieve and reason over information buried deep in its long-term memory. We are seeing a move toward linear attention and state space models like Mamba to overcome these limits. The core issue is that transformers are essentially reactive token predictors. They lack a persistent world model or an internal workspace to iterate on thoughts before expressing them. To reach the next level, we must move beyond the flat layers of attention. Is there a way to make models think before they speak? The answer lies in how we spend our compute, not just in training, but in the moment of inference. The most profound shift in 2025 and 2026 is the rise of inference time scaling. Instead of just making the model larger during training, we are now giving it more compute at the moment of the query. This is the paradigm introduced by models like OpenAI's O1, where the model uses reasoning tokens or thinking time to explore multiple paths before providing an answer. By scaling compute during inference, we can achieve high-level reasoning on smaller, more efficient base models. This effectively breaks the traditional scaling law that tied intelligence solely to parameter count. It's no longer just about what the model knows from its training data, but how well it can search for a solution in real time. This search vs learning trade-off is the new frontier of AGI. This approach mimics human deliberation, but how do we formalize this transition from intuition to logic? Let's analyze the psychological bridge between token prediction and actual reasoning. To understand the path to AGI in 2026, we must use the framework of System 1 and System 2 thinking. Standard LLMs are System 1, they are fast, intuitive, and excel at pattern recognition, much like our subconscious. But they lack System 2, the slow, deliberate, and logical reasoning we use for complex problem solving. The reasoning token revolution is our first successful attempt to implement System 2 in silicon. By allowing the model to self-correct, backtrack, and verify its own logic during inference, we are moving from stochastic parrots to reasoning agents. This transition is the true bridge to AGI. It means the model doesn't just predict the next likely word, it understands the logical constraints of the goal. As we master this, we move from passive assistance to active agents capable of multi-step planning. But this raises a new question. If models can now reason like humans, how will they differ in their fundamental approach to reality? In the next chapter, we explore the great schism between the different paradigms competing for the soul of AGI. To understand the roadmap to 2026, we must first address the fundamental divide between the pioneers of deep learning. Geoffrey Hinton, the godfather of AI, represents the connectionist Sutton-esque view, the belief that scaling laws are effectively a law of nature. From this perspective, the transformer architecture combined with massive backpropagation and compute will eventually emerge with biological-level intelligence. Hinton argues that LLMs do not merely predict words, they develop internal representations of the world to make those predictions accurate. In this paradigm, AGI is a matter of more parameters, more data, and more compute. However, this relies on the assumption that reasoning is an emergent property of scale rather than a separate architectural requirement. The industry is currently betting trillions on this scaling is all you need hypothesis, yet we are seeing diminishing returns in raw logic. But wait, is pure scale really a substitute for physical world intuition? One of the founding fathers of AI argues the exact opposite. In stark contrast, Yann LeCun, Meta's chief AI scientist, views current LLMs as a dead end on the path to true AGI. He argues that autoregressive models are fundamentally limited because they lack a world model, they don't understand cause and effect, gravity, or the physical constraints of reality. LeCun's vision centers on JEPA, or Joint Embedding Predictive Architecture. Unlike LLMs that predict every pixel or word, JIPA aims to predict abstract representations, mirroring how a child learns by observing the world without being told every label. This is the quest for objective-driven AI that can plan and reason within a mental simulation of the environment before acting. Without this, LeCun argues AI will remain a sophisticated parrot rather than a sentient agent. The clash isn't just academic. It determines where billions of dollars in venture capital flow. Let's map out how these two paths are actually converging in the latest lab results. What we are seeing in 2025 and 2026 is not one side winning, but a grand synthesis. Leading labs like OpenAI and Anthropic are moving towards System 2 reasoning, which integrates Hinton's scale with LeCun's requirement for internal validation. This is visible in models that use chain-of-thought processing at inference time, effectively allowing the model to think before it speaks. We are transitioning from simple probability to structured search, treating AGI as a problem of finding the correct path in a possibility space, much like AlphaGo did for games. This synthesis is driving R&D funding into verifiable AI and inference time scaling, where we spend more compute on thinking than on training. This ideological collision has created a structured roadmap for AGI development that every technical leader must memorize. Regardless of which school of thought wins, the industry needs a standard to measure progress, leading us to the critical 5 levels of AGI maturity. As we navigate this schism, the industry has converged on a maturity framework to define our proximity to AGI. Level 0 represents legacy AI static, task-specific algorithms with no conversational ability. Level 1 is where we spent 2023 and 2024, era of chatbots. These models exhibit fluent language but are prone to hallucinations and lack reliable multi-step logic. As of late 2024, we have officially entered Level 2, the reasoners. These models, like OpenAI's O1 series, can solve complex math and coding problems by evaluating multiple hypotheses internally. The shift from L1 to L2 is critical because it moves AI from a probabilistic guesser to a logical validator. However, even a reasoner is still trapped in a chat box, waiting for a human prompt. Climbing from a mere chatterbox to a reasoner is one thing, but the real economic explosion happens at the next stage, where AI begins to act independently. Level 3 is the agentic phase, which defines the 2025 landscape. Agents don't just talk, they execute. They can browse the web, use APIs, and complete multi-day workflows without constant human oversight. To reach Level 3, a model needs reliability and agency, the ability to self-correct when a tool fails. Beyond this lies Level 4, the innovators. This is the holy grail where AI begins to aid in scientific discovery, formulating new hypotheses that humans haven't considered. Level 4 models won't just write code, they will design new computer architectures. Moving from L3 to L4 requires a fundamental shift in how we handle out-of-distribution data, the ability for the model to think outside the boundaries of its training set. If Level 3 is about action, Level 4 is about creation, but many experts argue that we are hitting a massive technical wall that no one wants to talk about. Reaching Level 4 and the ultimate Level 5 organizational AGI is surrounded by myths. Many believe AGI is a single software update away, but technical barriers like the data wall and energy constraints remain significant. There is a common misconception that AGI requires consciousness. In reality, AGI is defined by functional competence, doing what a human can do, regardless of internal experience. We also face the alignment problem, where an autonomous innovator might solve a problem in ways that are harmful to human intent. As we target 2026, the focus is shifting from how big is the model to how capable is the system. Level 4 isn't just about intelligence, it's about the reliability of that intelligence in high-stakes environments. With the theoretical framework of AGI set, we must now look at the specific mechanism turning these models into actual employees, the shift from static LLMs to autonomous agentic workflows. While scaling laws traditionally focused on training compute, the paradigm has shifted toward inference time scaling. Simple next token prediction often fails at complex logic, leading to what researchers call the stochastic parrot trap. To overcome this, we utilize reasoning chains like chain of thought and tree of thought. These methods simulate System 2 thinking, allowing the model to decompose a single query into a logical sequence of sub-problems. In the 2025-2026 landscape, state-of-the-art models like Fable 5 demonstrate that spending more compute during the thinking phase can yield performance gains equivalent to orders of magnitude more training data. This architectural shift represents the move from intuitive responses to deliberative problem-solving, but reasoning alone is a solitary act. What happens when one mind isn't enough for a global enterprise task? In the professional field, we no longer rely on a single gut model for everything. Instead, we are witnessing the rise of multi-agent orchestration. Think of this as a corporate hierarchy. A manager agent breaks down the project, a coder agent writes the script, and a validator agent audits the output against security standards. This swarms approach, popularized by frameworks in the 2026 era, mitigates the limitations of individual context windows and specialized knowledge gaps. By assigning distinct personas and tools to different agents, we create a resilient ecosystem capable of handling end-to-end workflows that previously required entire human departments. Cooperation is powerful, but it also amplifies mistakes. How do we ensure these agents don't hallucinate each other into an infinite loop? Reliability is the holy grail of the agentic shift. In 2026, the most robust systems utilize self-correcting loops. Instead of a linear output, agents operate in a RAG pattern reasoning followed by acting and then observing the result. If a Python script fails, the agent reads the traceback, hypothesizes a fix, and tries again. This self-reflection mechanism significantly reduces the hallucination rate for complex tasks. Technically, this is implemented as a recursive loop where the agent's own output is fed back as new context. This mimics the iterative debugging process of a human engineer, ensuring that the final deliverable has been stress-tested by the model itself. We've fixed the brain, but a brain without a long-term memory is just a sophisticated calculator. Let's see how they remember. As we move toward AGI, simple RAG retrieval augmented generation is no longer sufficient. We are transitioning to graph memory or RAG 2.0. Traditional vector search treats data as isolated points, but graph memory maps the intricate relationships between entities, concepts, and historical actions. This allows agents to maintain state over months, not just minutes. For instance, an agent assisting a legal firm must remember not only the current case files, but also the evolving relationships between past rulings and current evidence. By utilizing knowledge graphs, agents can perform long-term planning, identifying dependencies and potential bottlenecks in a complex project months before they occur. Memory is useless if you can't reach out and touch the world. How do agents actually execute commands? The true agentic shift happens when models move from talking to doing. This is achieved through tools used via standardized protocols like the Model Context Protocol (MCP). Agents are now equipped with hands APIs that allow them to query SQL databases, send emails, or even manipulate legacy GUI software using computer vision. This is the actuation layer of AGI. In a 2026 enterprise scenario, an agent doesn't just write a report. It gathers real-time data from ERP systems, performs a SWOT analysis in Excel, and presents the findings in a generated slide deck. This autonomous interaction with digital infrastructure transforms AI from a consultant into a collaborator. With power comes risk. Giving an agent right access to your production database is terrifying. So how do we stay safe? Safety in the agentic era requires more than just content filters. It requires operational guardrails. We implement frameworks like the NIST AI Risk Management Framework and ISO 4-2001 to govern autonomous actions. The core principle is human-in-the-loop (ATL) for high-stakes decisions combined with sandboxing for execution. When an agent requests a database write or a financial transaction, a control layer intercepts the call, verifies permissions, and asks for human confirmation if necessary. As we look toward 2026, these safety protocols are not just ethical requirements, but business necessities for technical reliability. We have covered the brain, the hands, and the safety net. Agents are the workers, but they need an office next. We look at the enterprise architecture of 2026 to see where they live. In the enterprise world, the all-in cloud strategy for AI is hitting a wall. As we approach 2026, the architectural standard is shifting toward a hybrid LLM approach. Large enterprises cannot afford to send sensitive trade secrets to public frontier models like Fable 5 or GPT-Next due to data residency and compliance risks. Instead, we see the rise of a layered stack where a massive, reasoning-heavy frontier model handles complex logic, while a small language model, or SLM, resides on-premise for high-speed, secure, and repetitive tasks. This architecture ensures that high personally identifiable information never leaves the secure perimeter. By decoupling the reasoning engine from the data repository, architects can swap models as the scaling war evolves without refactoring the entire business logic. This is not just a technical choice. It is a strategic maneuver to maintain data sovereignty in an era where data is the only moat left. But how do we decide which query goes where without exploding our operational costs? The answer lies in the orchestration layer, which we will examine next. Cost orchestration is no longer just about choosing a cheaper API. It is about semantic routing. In a production environment with millions of requests, sending a simple summarize this email task to a high-reasoning model like O1 or Fable 5 is a financial disaster. The 2026 strategy involves a pre-processing step where a router model, often a tiny, fine-tuned BERT or a 1 billion parameter model, classifies the intent and complexity of the incoming query. If the query requires multi-step deduction, it is routed to the frontier tier. If it is a retrieval augmented generation task, it goes to a specialized RAG engine. This process also includes token auditing to prevent runaway costs from autonomous agents performing recursive loops. We are moving from static endpoints to dynamic execution paths where the cost per query is optimized in real time based on current token spot pricing and server load. However, cost is only one half of the equation. We must also consider the geopolitical landscape of where this data physically resides. Teaser: does sovereign AI offer the same performance as global giants? Let's compare the metrics. As global tensions rise, sovereign AI has transitioned from a buzzword to a procurement requirement. Governments and heavily regulated industries are demanding models that are not only hosted locally, but are also trained on culturally and legally specific datasets. In this table, we compare the global frontier approach with the emerging sovereign model. While global providers offer unmatched general intelligence and massive scale, sovereign AI focuses on legal alignment and infrastructure autonomy. For instance, a sovereign model in the EU might be fine-tuned specifically on the EU AI Act's compliance requirements, outperforming a generic GPT-5 in regulatory tasks. The trade-off is often a higher initial capex for the local infrastructure compared to the OPX of cloud APIs. Architects now evaluate their geopolitical risk score when designing AGI-ready systems. Now that we have the infrastructure figured out, what happens when the scaling laws for raw data finally hit the ceiling? Question: where will the investment flow in 2027? Looking toward 2027, the industry is bracing for a pivot. The brute force scaling of 2023-2025, which relied on simply adding more H100s and more web data, is yielding diminishing returns. We are entering the System 2 era. Venture capital is shifting away from generic model providers and toward vertical AGI and reasoning efficiency. The mind map of 2027 shows three primary branches. First, compute efficiency, moving beyond transformers to architectures like Mamba or liquid neural networks. Second, synthetic data pipelines, using models to teach other models as high-quality human text runs dry. Third, agentic infrastructure, the plumbing that allows AI agents to interact with legacy SQL databases and ERP systems autonomously. This shift marks the transition from AI that talks to AI that reasons and acts. If the raw intelligence plateaus, the value moves to how that intelligence is applied to physical and economic systems. This transition will fundamentally rewrite the job description of every software engineer. In an agent-dominated ecosystem, the role of a developer is morphing into that of an agent architect or semantic engineer. Writing syntax is becoming a low-value skill. The new checklist for relevance includes mastering agent observability, being able to debug why an autonomous agent made a specific decision. You must move from being a coder to a verifier. This involves designing robust evaluation frameworks (EVALs) that test the limits of model reasoning before deployment. Furthermore, understanding the semantic layer, how to structure enterprise data so an LLM can understand the context of a table without manual mapping, is the new SQL. We must also focus on human-in-the-loop design, ensuring that as agents take more control, there are still intuitive kill switches and verification checkpoints. This isn't the end of programming, it's the beginning of high-level logical design. Question: but will the law allow these agents to act freely? The regulatory hurdle is the final gatekeeper. The final piece of the 2026 matrix is the regulatory landscape. The EU AI Act is the first of many frameworks that will treat general-purpose AI with high risk. By 2026, companies will be legally liable for the actions of their autonomous agents. This means explainability is no longer a research goal, it is a legal requirement. If an agent denies a loan or makes a medical recommendation, the system must provide a human-readable audit trail of the reasoning path. We also anticipate a push for watermarking of all AI-generated content and strict copyright licensing for training data. These regulations will slow down deployment speed but increase the stability of the ecosystem. As we wrap up this chapter on enterprise strategy, we realize that the technical, economic, and legal threads are now inextricably linked. In our final chapter, we will synthesize all these frontiers into a single, unified roadmap for building in the age of AGI. Next up, the synthesis. As we conclude our deep dive into the 2026 AI landscape, we must synthesize the three layers of understanding required for a technical leader or professional engineer. At the conceptual level, we've moved beyond simple scaling laws to a dual scaling paradigm, pre-training compute and test time compute, as evidenced by OpenAI's O1 and recent Fable 5 benchmarks. Structurally, the industry is shifting from monolithic LLMs to multi-agent systems and System 2 reasoning architectures that prioritize logic over mere token prediction. The impact is a fundamental change in enterprise architecture, where the agentic workflow becomes the primary unit of productivity. To master this, you must understand the interplay between chinchilla optimality and the recursive self-improvement loops that will define AGI 2026. This systematic view transforms a chaotic trend into an actionable roadmap. But wait, even with this map, why do most enterprises fail during the transition? Let's reveal the single most important pivot you must make in our final summary. The most critical takeaway for the year 2026 is that structural innovation now carries more weight than raw scale. While the giants continue to build massive clusters, the real competitive advantage lies in architectural efficiency, the ability to achieve AGI-level reasoning through modularity and feedback loops rather than brute force parameters. As many industry pioneers have noted, we are hitting the data wall for human-generated text, making synthetic data and self-play RL the only viable paths forward. For an architect, this shifting focus from how large is the model to how robust is the reasoning engine and how autonomous are the agents. Success in this new frontier requires a shift from being a consumer of AI to being an orchestrator of intelligence. Mastery of these principles is what separates a technician from a visionary. This marks the end of our deep dive into the 2026 AGI horizon, but for those who master these frameworks today, the real journey into the post-AGI economy is only just beginning.